Welcome, ladies and gentlemen, to this presentation about the Precision Engineering and Metrology Group's work on industrial robotics. My name is Nicholas Tyson, and I have the pleasure to present this work to you together with my colleague Monica Gonzalez, who will demonstrate to you how we use our research to improve the positioning accuracy of industrial manipulators. We are both PhD students of Andreas Akenti. With that, let's get started. Today's presentation focuses on our research areas, current projects, as well as future work. We will present to you our work on physics-based robot calibration, that is the process of describing the pose, that is the combined position and orientation of the manipulator's end effector, as a function of its kinematics, statics, dynamics, and thermoelasticity. Then, my colleague Monica holds a demonstration on how we use the calibrated manipulators for force deformation compensation in an interaction with its environment. Let's start with the research areas. Physics-based robot calibration. KT's aims in physics-based robot calibration are to provide pragmatic offline calibration procedures for kinematics, statics, thermoelasticity, which can be used by industrial practitioners, and to develop online calibration procedures and hardware for kinematics, statics, and thermoelasticity, which can be used by robot OEMs such as ABB. To give you an example what we mean by that. We all work with the kinematics of industrial manipulators. That is, we describe the position and orientation of the end effector as a function of, for example, its Dennawitz-Hartenberg parameters. We know that there's a difference between the design Dennawitz-Hartenberg parameters or the nominal Dennawitz-Hartenberg parameters and the actual Dennawitz-Hartenberg parameters. What usually is done is that an individual robot is being measured in order to compensate for that difference, and that is what you see on the left-hand picture, what we are currently trying to do using commercially available sensors integrated into the box, which is mounted on the end effector of the industrial manipulator. Then there's thermoelasticity, which is the study of how aspects such as kinematics, statics, and dynamics change as a function of temperature. And what you see on the picture on the right-hand side is how we have visualized the temperature gradients and measured the temperature of a certain link of the industrial manipulator in order to compensate the kinematic parameters of the industrial manipulators for the temperature as a result of the task program of the industrial manipulator. Our main focus, though, is the interaction of the industrial manipulator with its environment in either static, quasi-static, or dynamic applications. This video shows you some of our measurements that we have conducted in 2018 at ABB, and you will see a similar procedure being demonstrated to you by my colleague Monica, which focuses on the calibration of the industrial manipulator's compliance under motion. This is an example of how we also measure the dynamics of industrial manipulators, where on the left-hand side you see a visualization from the measurement, and on the right-hand side you see the same result or the same dynamics of the industrial manipulator being modeled at ABB in order to give them the opportunity to compare also the validity of their models under load. Let's turn to the demonstration.
This demonstrator is part of an ongoing work to develop an online compensation algorithm for improving the positioning accuracy of industrial robots in machining operations, in which they are subjected to significant loads due to the interaction with their environment, while they have to maintain tight geometric dimensions and tolerances. The setup presented in this demonstrator is comprised of the robotic system, an IRB 6700 ABB robot with its controller, the loading system, an LDBB loaded double ball bar, a device which is used in performance evaluation of machine tools with integrated capabilities to apply static loads and measure distances in micrometer accuracy and submicrometer precision. The forces are measured using an HPM force torque sensor mounted on the robot's end effector. An LVDT, which is embedded in the LDBB, and a Leica AT901 laser tracker are used for validation. And finally, the compensation system, which collects the data from the sensors, performs the signal processing, computes the respective compensation that must be applied based on previously identified physical properties of the robot, such as the Navier-Hartenberg parameters and joint stiffness values, and communicates the values to the robot controller to perform the compensation. For the demonstration of the online compensation strategy, the robot follows a circular low-speed trajectory at 50 millimeters per second to create a so-called quasi-static loaded trajectory. The experiment measured the path positioning accuracy along the trajectory for an unloaded case, a loaded case, and a compensated case. In the case of the loaded and compensated cases, the placement of the LDBB having an angle with the horizontal plane or XY plane ensures that the robot is loaded in the three Cartesian directions throughout the movement execution. The approach of a quasi-static trajectory is emulating the interaction of forces at movement during the actual machining process. Now, let's see the compensation in action. So far, what has been achieved from this online compensation process can be seen in this picture. The no-load case or unloaded case corresponds to the blue line or the blue circle. The loaded case corresponds to the orange circle, and the compensated case corresponds to the yellow circle. For this case, where the magnitude of the load applied was around 500 newtons, the average deformation was reduced from around 1.5 millimeters to 580 micrometers. Currently, we are still working on improving the compensation to achieve a 250 micrometers target, reducing the processing time and the synchronization of the algorithm, as well as considering the influence of different variables in the quasi-static stiffness identification and overall compensation performance.
Current projects. COMAC, Clean, Precise and Defect-Free Composite Parts Machining Robot. COMAC project answers the needs of composite part manufacturers to increase the competitiveness of the industry by proposing the development of a cost-effective and flexible robotic solution for the machining of composite parts, including an internal dust suction system for improved health and safety conditions, reduced energy consumption, increased precision, and continuous process monitoring for right the first time machining. The main objective of the project is to enable the machining of carbon fiber composite materials for industrial manipulators in the aerospace, automotive, and energy provision industries. The Swedish partners, that is ABB, Hexagon, and KTH, focus on two main goals, that is, to improve positioning accuracy through quasi-static manipulator calibration and to create design knowledge for industrial manipulators in contact applications. Platforms. SharpCut is a modular simulation platform for machine tools and industrial robots. SharpCut has a library of calibrated machine tools and manipulators, as well as force prediction and path planning models to optimize trajectories for task programs. The video shows how SharpCut is also used in education. The video shows a mobile phone application developed for the visualization of kinematics, statics, and thermoelasticity on the positioning accuracy of an industrial manipulator. The application has been developed in the Unity game engine designer. Collaborations. Telesurgical robotic systems allow surgeons to perform surgical operations from remote locations with enhanced comfort, dexterity, and accuracy. Telesurgical robotic systems are capable to assist in a wide range of surgeries such as orthopedic, gynecologic, cardiothoracic, and general surgery, with several applications such as laparoscopic procedures, eye surgery, and fracture manipulation. Cost reduction have a great potential for future research in that field. One potential cost reduction comes from economies of scale through the application of off-the-shelf industrial manipulators. For the repositioning of bone fractures, KTH and Tokyo University would like to exploit physics-based calibration of industrial manipulators in combination with on- and offline compensation to improve the positioning accuracy. In addition to that, Tokyo University and KTH would like to review the development of the positioning accuracy of industrial manipulators to assess the feasibility of their application for different areas of surgery. Future work. Finally, for our future work, we would like to highlight our publication roadmap related to industrial manipulators. The main focus lies on being able to perform the developed calibration procedures using sensor-based measurements as presented in the slide on physics-based calibration to reduce the need of expensive measurements instruments and be able to continuously acquire data for condition-based monitoring. There are currently no planned further projects on robotics. We plan to apply in 2021 together with Tokyo University in a project focusing on industrial manipulators in surgeries. However, due to the current situation, that is uncertain. Thank you very much. This ends today's presentation and demonstration, and we would like to answer your questions. And as always, would like to end on the note of perhaps the most fundamental question one can ask about a robot is, where is it? Thank you very much.